Welcome to this last lecture of week 2. In this we will be talking about the kinetics of the adsorption. Now it is often conceived that although adsorption is an equilibrium process, why does the kinetics is important to study? Now this kinetics is often important for systems where this is the adsorption is limited by many times with mass transfer, or the adsorption is very slow and there are other simultaneous transport phenomena, either diffusion or chemical reaction which takes place, and in that case kinetics of this adsorption becomes very important as it becomes a rate governed process. Now coming to the kinetic models, there are several models. We will of course talk about them in this class itself, but before that I want to introduce that, or I want to emphasize that the kinetic study is done till the state when the concentration of the adsorbate reaches the equilibrium value. So please note for the case of the isotherms, you prepare or you try to do an experiment to find out the equilibrium concentration of the adsorbate for different levels of the concentration, whereas in the case that could be either by changing the amount of the adsorbent that you are adding, or by increasing or changing the initial concentration of your solutions. In that way you can actually tweak the relative uptake of the solution. But in the case of the kinetics, it is a time dependent situation. So for a particular sample you start with the initial concentration and then you track the change in the concentration in the solution phase with respect to time, and from there you can work out what would be the concentration of the adsorbate in the adsorbent with respect to time, and then again how these two are related. So here during the kinetics it is generally the concentration in the solution phase is measured with respect to time, starting from an initial concentration till it reaches an equilibrium, right. So just to be clear, I mean, or I refer to the following situation, that in the case of the kinetics this is often confused, that in the case of the kinetics of the adsorption, one measures the concentration of the adsorbate in the solution phase with respect to time. So this decreases and slowly it trades off to an equilibrium value, whereas the concentration profile in the adsorbate is increasing and then slowly it attains a steady state value, right. So this is what we do, or what is measured in the kinetics. In the case of the isotherm, it is the equilibrium scenario. So in that one measures the different, or one estimates the different equilibrium concentration, and from there you try to work out or try to relate the equilibrium concentration in the adsorbent phase, and that follows this trend. So this is at equilibrium or when t tending to infinity. Okay, so this is what we generally refer in the isotherm, but in the kinetics you measure the time dependent concentration profile. So this actually starts from an initial value of, let us say, C naught. So initially the Q value is 0, so at time t is equal to 0 the Q value is 0, because there is no adsorption or no concentration of the adsorbate in the adsorbate phase. Now we see first the Langmuir kinetics. So the Langmuir kinetics is actually derived from the equilibrium relation, and until an equilibrium is reached, the difference between the rate of adsorption and the desorption would be non-zero, right, and these two rates wouldn't be equal. It is only at the equilibrium they are equal. So, at before equilibrium these two are not equal, and essentially the difference between these two rates is represented by the accumulation term. So, this dq dt is equal to the rate of the forward process minus the backward process. So, the forward rate constants can be represented as something like this. So, this equation you realize that for t tending to infinity, dq dt tends to 0, and that is where you attain equilibrium scenarios. And in that case, if you rearrange the equations, you will be getting so this represents q is equal to so this is the equilibrium isotherm expression. So, at equilibrium when dq dt approaches to 0, q approaches to the equilibrium. So, this is the situation at equilibrium, and you recover the equilibrium expression. So, if you know the Langmuir isotherm is applicable for your adsorption system, then it is advisable that for the kinetic process you try to use the Langmuir kinetic models. Of course, the Langmuir kinetic model can also be expressed by the other non-linear or the pseudo Lagrangian models, which we will introduce immediately. So, the other kinetic models that do exist, which are all inspired from chemical reaction rate theories. So, for the case of a simple 0th order kinetics, which suggests that this dq dt is essentially constant. So, let us represent the constant by C0. So, this integrated form of this expression q as a function of t takes like this two constants. So, I mean this is evaluated at t is equal to 0, q is equal to q0. So, obviously, this tells you, I mean this order model cannot predict the equilibrium behavior, because this is closely related to the situation for initial times, because when t reaches infinity, that q does not achieve equilibrium concentration, instead q also becomes unbounded on infinity. So, this model, as you can understand, is only to explain the initial trend. For example, here when the profile of q with respect to time is linear. So, in the linearized zone or in the zone initial time, this 0th order model is generally very good to explain this behavior. Coming to the other versions, that is the first order model. So, the first order model is very similar to first order rate equation. So, the integrated form of this equation takes this form. So, this factor of 2.3 comes from the fact that you convert ln to log. Here this also, even though this can explain the nonlinear trend of the, so this is like the nonlinear trend of q as a function of time can be tracked from this model. So, this can explain the situation beyond the initial time phase or the initial time period, but this also does not capture the part or this phenomena that for when t tends to infinity, that q should approach the equilibrium value or the equilibrium concentration in the adsorbent phase. So, to consider, I mean, to bring into this idea, pseudo first order models has been proposed, and these are generally quite effective in capturing the nonlinear trend as well as the equilibrium value at large times or close to the equilibrium scenario. So, in this case, the dq dt model is represented as like this. So, you can clearly realize that when t tends to infinity, q approaches to qe, even if I do not write the integration integrated form, still it tells us that when this model, when t tends to infinity, dq dt tends to 0 and naturally q approaches to qe. This is of course not true for the previous 0th order and the first order model. So, the integrated version of this looks something like this, and from here also you can realize that when t approaches to infinity, q also approaches to qe. Next, we have the second order models. So, the second order models is again inspired from the second order chemical reaction rate q square, and this integrated form of this expression looks like this. So, q0 is the initial value, and here also you see that interestingly this q is inversely proportional to this time. So, which suggests that as time is increasing, q is decreasing. So, this is a very important phenomena that you can observe here, that in the case of the second order model, which is not very usual to see that with the increase in time, it is found out that q is actually decreasing, or these are inversely proportional. Of course, that can be moderated with the value of q naught in this case, but naturally the trend of the profile suggests that q is decreasing, and this is a very specific observation in this case. So, normally second order models are not very popular or very widely used, and it is only in very few circumstances the second order model is actually applicable, particularly when there is additional mass transfer effects which actually affects the adsorption besides being a purely adsorption based phenomena. There is also the existence of the pseudo second order model, which is represented as this. So, in this case also, as t tends to infinity, q approaches to qe. So, this also captures the equilibrium behavior in the long term or close to the equilibrium, and in this case the integrated version is like this. So, here also the same trend is there, but interestingly the QE values are nicely captured in this case, and the system tend towards the equilibrium values at long times. But here also one can observe that with increasing time the QE values Q values are not proportional, and this is something that is very interesting for this system. Now, there is one more kinetic model which is known as this Elovich theory. and this is exponential format. So, in this case the integration form makes this shape. So, this is also a highly nonlinear process, and this is particularly useful to predict the adsorption behavior when the kinetics is very slow. So, LH is very good when kinetics is slow, or the adsorption kinetics is the rate determining step in the transport phenomena of the system. Now, this and of course, this is nonlinear in nature too. So, except the 0th order model, all the other models, first order, second order, then you have this pseudo first order, the pseudo second order, all of these models are nonlinear in nature. These kinetic theories, particularly the pseudo versions, the pseudo first order and the pseudo second order, were actually proposed or originally proposed by this Legagran theory. So, Legagran actually proposed these pseudo order models to take into account that this kinetic behavior should approach the equilibrium values at long times or at large times, which is not existence in the classical rate expressions or the rate theories. So, now it is understood that the kinetics of the adsorption also plays a important role, particularly in situations when the equilibrium value is takes a considerably a finite time which is comparable. I mean, the time scale of the adsorption, if it is comparable with other phenomena, for example diffusion or chemical reaction, then this is an important aspect of the problem or the coupled physics of the system, and kinetics needs to be evaluated. So, the kinetic theory helps us to relate how does the concentration in the adsorbent phase actually changes with respect to the time. There are several different theories. The 0th order model explains the linear regime, which is generally true for small time. The first order models captures the nonlinear behavior. I mean, both the first orders and the pseudo first order captures the nonlinear behavior, but particularly the pseudo first order model takes into account of the fact that this equilibrium concentration is attained at large times. The second order models is slightly different than the first order, as in this case you can see from the expression that with increasing the time, the concentration profile may the concentration or the adsorption in the adsorbent may decrease depending on the capacity of the adsorbent. Similarly, for the case of the pseudo second order, even though it approaches the equilibrium value, the trend of the adsorption profile may be different than the first order or the 0th order model. The LH theory captures the kinetics for slow behavior, or when the kinetics is very slow, and in this case this Q or this adsorbate concentration in the solid phase varies with respect to the time in the logarithmic scale. So, these are the different adsorption models that are present and that are widely used to study this behavior of the kinetics. In general, if many a times it is observed that the kinetics do not follow either a 0th order or a first order model. So, in that case, for nth order kinetics, when n is not equal to 1, the generalized kinetic expression can be written down as, I am writing the pseudo version, something like this. So, this pseudo nth order kinetic expression can be expressed in this form. This is a 3 constant model expression. So from the plot of your q versus t, you can work out what would be these kinetic constants, and generally the equilibrium value is known before. So this the only two constants in this model, whether it is 0th order, first order, second order, pseudo first order or whatever, is actually plotted from this expression of the values of log of dq by dt with respect to q. So in this case the QE values, QE is known, are known, and are known from the fact that if you allow this equilibration to happen, you can know what is the equilibrium concentration. So that is generally the equilibrium concentrations are known for any kinetic experiments, and from this plot of this log of dq by dt versus q, generally the profile in this case is I mean it is better to write log of QE minus Q, and in this case the slope represents the value of the n, and intercept represents the value of log of Cn. So from this expression or from this correlation, you can work out what would be the constant or particularly the exponent, whether it is close to first order or second order, can be worked out by analyzing the kinetic data from your experiments, provided the values of QE are known already, and which is easily available since QE is the equilibrium concentration, and that is obtained at large times for any kinetic experiment. So I hope all of you have got a fair understanding of the kinetics, particularly when the kinetic theory is important for your case, and it is also relevant to realize that the kinetics does play an important role, particularly when there is another transport phenomena happening along with adsorption. So the different kinetic theories that has been explained here pertains to different types of scenario involving different physics or different adsorbent interactions in different scenarios, whether it is gas or whether it is liquid, solids, organic molecules, gaseous molecules, inert molecules. The kinetic theory does hold for different types of system. I hope all of you have found this information and this lecture contents useful. See you all next week.